Okay, right, let's have a look at this. So one of the things we need to consider is how strong is a magnet? And more importantly, how can we tell how strong a magnet is? Well, if we were thinking about the field lines, well, if they were closer together, then we had a stronger magnetic field. Now, a more technical way of talking about field lines is to talk about magnetic flux. Now, a way of thinking about magnetic flux is it's just the number of field lines. When we talk about magnetic flux again in a few lessons' time, we'll be thinking more about the number of field lines through an area and the angle that that area takes through the field. But for now, we're just going to think of magnetic flux as being the number of field lines. And we give that a measurement. We use units of Webers. But really, all that's doing is it's quantifying our drawing of the magnetic field lines, these lines of flux. Because the magnetic field doesn't actually run along lines, the magnetic field is continuous. Because remember, magnetic field lines and magnetic flux lines, same thing, but all they are is a representation of the magnetic field. So really what we should be interested in if we're thinking about the strength of a magnet, we need to be looking at the flux density. How many of these field lines are there per unit area? And flux density, which has a symbol of B, helpfully, is measured in Teslas. Or Tesla. Okay. And a Tesla, all that is, Tesla is Webers per meter squared, because it's just the density of the flux, but this is sort of the flux cutting through an area. So although density, you might be thinking, oh, that needs to be meters cubed, 3D. No, this is going through an area. Okay, so that's how strong a magnet is. We need to be thinking about the flux density that a magnetic field, of the magnetic field that's being produced. And flux density is the number of flux lines, which is representations of the magnetic field per unit area. So how can we actually relate this notion of flux density to reality? How can we actually get a measure of it? Because at the moment, flux lines are just lines we draw on a piece of paper to represent a field. So how can we know how many lines we need to draw on a piece of paper? How can we tie this to reality? Well, we can do this through an experiment that makes use of Fleming's left-hand rule to bind these things together. Because if you think about Fleming's left-hand rule, we've got three elements. We've got the force that is produced. So in Fleming's left-hand rule, that would be the thumb. We have the external magnetic field, which is the flux density, and we have the current. All of these being at right angles to one another. So if we think about that, we've got the force, we have the field, and we have the current. So here we have a relationship that is binding together several things, and many of these we can measure. So if we can measure all but the external magnetic field, that means that we can experimentally calculate what the external magnetic field is going to be for any given magnet. So what we need to do is we need to have a setup where we can measure this. So if we think a little bit more about what's going to happen. So if we've got our north and south, we're going to have our externally applied magnetic field going between them, and technically I should have done this as a uniform field, so they should all be the same distance apart, even though they're not. Then if we put our current carrying wire in the middle, so we just see the point that indicates that the current is coming out of the page. Okay, that's going to generate a magnetic field around it that we can find by using the right hand screw rule. So it's coming out of the page, it's going to wrap around in that direction. Okay, and bear in mind this is just a representation of what the field would be if there wasn't another field in the way, because what have I done? I've cut across field lines. This is a representation of what the two fields would be if they existed in isolation. If they did not exist in isolation, then we'd have to draw the field lines more like this. They would be diverted in a similar sense to how if you had two magnets repelling each other, you would draw them pushing each other apart. Okay, so that's why that would be like that. And then they're going to apply a force on this wire due to the two fields, which is going to move it up. So here we have our external magnetic field. We have our applied magnetic field due to the current, because the current's going in that direction. And then we have the force that this would produce. So hopefully what you have learnt from GCSE is you have learnt the equation that relates these three things together. And actually a fourth one gets added in. F is equal to Bill. So here we have our force measured in newtons. We have our flux density measured in Tesla. We have our current in amps. And finally, we have the length of the wire, and that's in meters. It should hopefully make sense why length of wire is in there, because we're talking about the force on a complete wire, and so the force is going to be greater if more of the wire is in the magnetic field, because there's more interaction going on. There are more cross-cutting sections, so if flux density is being magnified over a length, then it's going to be a greater force. Okay, so this is our equation. So because we've got an equation, we have a relationship. That means that we can create a new equation to try and find what the flux density is going to be. So if we just rearrange that, flux density is going to be the force divided by current over length. So we've already said that 1 Tesla is Webers per meter squared. We have a new equation that we could then break down into base SI units, being that a Tesla is going to be newtons per amp meter. Okay, so this is just one of the ways that if you ever get a question where it's break this down into base SI units, well, that's your starting point, because then you can further break the newtons down. Okay, so how could we look at this experimentally? Well, we could use a setup like this. Now, it's very hard to directly measure the force of something. We are usually measuring it by some sort of proxy. So in a Newton meter, that's the extension of a spring. But again, that is using other constants. So in this case, we're going to be using a mass balance, which is just an electronic version of a spring, really. So it's calibrated for Earth's gravitational field strength to say, right, if this force is applied to this mass balance, I'm going to record it as being this mass once I've done the calculation. And we'll look at that calculation later. But in essence, what we've got is we've got our two permanent magnets, which are producing a magnetic field between them. We have a wire, which is held between them by being placed in a block, with a current being passed through it. If a current is being passed through it in that direction, that means using Fleming's left-hand rule, we can identify that the force is going to be pushing down. Okay, so if we think about this experimentally, if we zero this when there is zero current, that means that when we apply a current through this, what we'll be measuring is the equivalent of force once we've done some calculations to it. Internal to the mass balance, it is doing some calculations. It is using the equation that F is going to be equal to m times g. And then what it's doing is it's actually sort of measuring the force, probably through a spring, and so using the equation of Hooke's law to try and work out what the applied force would be, and then it's displaying the mass. So if we keep this in mind then, as we're doing our other calculations, we can substitute this in later. So because we have zeroed it, all the force on that mass balance should be due to the interaction between the current carrying wire and the magnetic field. So the force on it should be equal to this. So we can measure that using the mass balance. We can't measure this one. We can measure the current using an ammeter, and we can measure the length of the wire using a ruler or other instrument for measuring distance. Because actually that's what's going on, and we're being displayed the mass, we need to say that mg is equal to Bill, because it's the apparent force. So then if we rearrange that, mg is equal to the current over that. Okay. But that's for a straight calculation. And in experiments, wherever possible, you want to relate things to a graph so that you can get multiple readings at multiple different stages and really test that relationship. So if we were to draw a graph of the recorded mass, which is relating to the force, against the current, it should have a reading something like that. Because as we increase the current, the force should increase on the wire, which should increase the apparent recorded mass. So that means that the gradient of this is going to be equal to the mass over the current, or change in mass over change in current. So if we put this into the equation, B is equal to m over I, being the gradient, and then we multiply that by g over L, we can see that if we take the gradient of that graph, which we found experimentally, multiply it by g over L, then we'll have found our field density and so the strength of that magnet. So that's how you can do this experimentally. Many sources of error in this, because you're using a stated value for g, and g does vary. You've measured L, you've measured something using a mass balance, so you've got all these different errors that could come in. Most of them, however, are going to be systematic errors rather than random errors, because you've got zeroing errors from the mass balance and you've got values of constants which can have errors associated with them. Now we get to the real step up from GCSE to A level, and that is, so far we've been assuming that the wire or the current is always perpendicular to the magnetic field. This isn't always the case. Wires can sometimes not be perpendicular to a magnetic field because reality. So we need to think about what the field would be in different cases, and then think how we could relate that in maths. So to start with, we'll think about the nice simple case. We have our magnetic field lines, and we're going to have our current. This one is perpendicular. And at this point, when theta is equal to 90, we have the max. So it is at a maximum when it's at 90 degrees, it's perpendicular. We're going to find our minimum when it is in parallel, because at this point there is going to be no interaction between them. There is not going to be a force applied. So here we have our minimum. So hopefully what this should be indicating to you is that sine might be involved in some way, shape or form. And so the new version of this equation for A level is F equals Bill sine theta, where the angle between the current and the magnetic field lines is the sine theta. So in this case, it's at its maximum. This point, it's at its minimum, and we can find it there. You could check this experimentally, but this is correct.